So we're going to talk about logarithmic functions today. Recall that an exponential function is a one-to-one function and therefore has an inverse. The inverse of an exponential is called a logarithmic function. So a logarithmic function with base b is a function of the form y equals log b of x, where x is strictly greater than 0, b is strictly greater than 0, and b is not equal to 1, and the equations y equal log base b of x and x equals b to the y are equivalent. Okay, so let me kind of translate all that. Let's start with what a logarithmic function even looks like. A logarithmic function is going to be something that's log y equals log base b of x. So there's going to be a number plugged in for b. That number has to be positive and it can't be 0. So maybe we'll see something like log base 3 of 7, or y equals log base 1/2 of x plus 3, something like that. So there's going to be a number filled in for the base. The x part, well, that might be a number or it might be a variable part. The part where the x is that's inside the parentheses is called the argument of the log. And those of you going on to trig or currently in trig hear me talk about the argument of the function all the time, which is what's inside the parentheses. I want to be very clear that this is not log times x. Just like f of x is a notation that always stays together, it never gets broken up into the f separate from the x. Log base b of x does not ever get broken up either. That's one whole notation. All right, so the argument has to be positive. There's a domain restriction. The argument has to be positive. The base is positive and not 1. And then the other big thing is the relationship between exponential form and logarithmic form. You know how we can convert notation back and forth between a rational exponent and radical form? That a to the m over n power can be rewritten as the nth root of a raised to the m. Well, that's the same thing that's happening here, where it says that these two are equivalent. The reason we can't just say equals is because they both have an equal sign in them. So I feel like they're writing them, kind of awkwardly. Y equals log base b of x can be rewritten as in exponential form, and that exponential form looks like x equals b to the y. That is what we're going to use over and over and over again for graphing, for solving equations throughout the rest of this chapter, which is the rest of this unit and whatever else is on the final. I always think of it kind of like a wheel. Now here you see I've flip-flopped it from here, that now the y is on the right. I kind of like it with the y on the right. I always remember that the exponential base and the logarithmic base are the same. So I'm going to start with the base, 3. And then I'm always trying to tie something new to something I already know. When we would convert a mixed number to an improper fraction, we always started on the bottom, right? And then we kind of go in this circle, 4 times 1 plus 3. Well, that's how I see this. I'm going to start on the bottom, and the lowest thing I see is my log base. So I'm going to start with the 3, and then I go in a circle. My exponential rewrite is going to be 3 squared equal to 9. So I don't know, that's just something silly that I do to help me remember it. We want to rewrite log base 16 of 4 equal to 1/2. The exponential base and the logarithmic base are always the same. So 16, And then I always remember the circle. 16 to the 1/2 is equal to 4. And those are our rewrites. Questions at all on the rewrite? Now I want to go the other direction, where I've given it to you in exponential form and I want you to rewrite it in logarithmic form. Personally, this is the harder direction for me, so I usually rewrite it as a log and then double check it using my little circle thing. I remember that my exponential base and my logarithmic base are the same. So what is our base in this next example? 81 equals 9 squared.
2. Is that what you mean?
We're looking for the base number. If I saw this number 2, I would call that an exponent, right?
Oh, yeah.
Yeah.
So we're looking for the base number, and the base is always what is being raised to an exponent.
So 9.
So 9 is our base here. So I'm going to start with log base 9. And because personally I'm more comfortable with my little circle thing, I always say, all right, 9 raised to what power equals? And then I know where to put things. So I know it's 9 squared equals 81. I know I've heard students lots of times say that they just always remember that the argument is the number that's all by itself, and that's fine. So if the two bases are the same and you remember that the argument is always all by itself, then you naturally know what the other number is. (1/49) equals 7 to the negative 2 power. What is our base going to be?
7.
7.
You got it. This becomes a log base 7 of 1/49 equals negative 2. Questions at all? In our next couple examples, we want to evaluate the given log exactly. Log base 2 of 1/2. Now, your knowledge of logs, well, is extremely little right now because I just introduced it for the first time. But honestly, your knowledge of logs compared to everything else is going to stay pretty limited. I feel like my knowledge of logs is very limited compared to everything else that I know about math. But our knowledge of exponents, I think, is pretty extensive. And we know that we can convert back and forth between logarithmic and exponential notation. So when we're asked to solve a problem like this, evaluate exactly, we're going to use our knowledge of exponents to help us answer this. So log base 2 of 1/2 is equal to, I don't know, right? I'm just putting a question mark. You can put a regular variable if you like, but I'm using a question mark. What we're going to do now is rewrite it in exponential form since we know a lot about exponents. Our exponential rewrite is going to be, remember our bases are the same, so log base 2, I'm going to start with exponential base 2 raised to the question mark equals 1/2. And now I'm just going to think about it. 2 raised to what power equals 1/2?
To divide negative first.
So I got to vote for 2 to the negative first. Let's just think about that. Oh, a negative exponent always tells us to take it to the other side of the fraction. So this becomes 1/2 to the first, which is indeed our 1/2. So our answer here log base 2 of 1/2 is equal to -1. The exponent is what we're looking for. Questions? All right, let's try the other one. We want to figure out what log base 100 of 10 is. We'll start by rewriting it in exponential form. What is the exponential rewrite going to be?
100 to the power of x equals 10.
I'm still going to use question mark, but yes. So the question becomes 100 raised to what power is equal to 10? So let's think about it. What relationship do we know between 100 and 10? And how is that relationship affected by an exponent so that we can make them equal to each other?
Well, 100 is 10 squared.
That is correct. So we're looking though for the exponent on 100 that would make them equal. You found me an exponent on 10 that would make them equal. So we want to know 100 raised to what power is equal to 10?
Half.
1/2. That's right. Remember that an exponent of 1/2 is the same as the square root, and we know that the square root of 100 is 10. Therefore, log base 100 of 10 is equal to 1/2, and 1/2 is our answer. Questions, anybody? There are two common bases that arise in logarithmic functions. These bases are base 10 and base e. The logarithmic function of base 10 is called the common logarithmic function. It's used a lot, most commonly. That's why we call it the common log. And it's denoted f of x equals log of x. So you'll notice that there's no little base number there. Just like the square root is the most common root radical, so we don't write the index of 2 in, same thing's happening here with logs. Since base 10 is the one that's used most commonly, they don't bother writing it and it's understood. The other one is when we have a logarithmic function of base e. This is called the natural logarithmic function. This arises a lot in nature. The e shows up. It is denoted f of x equals ln of x. So ln is our natural log. I always think to myself log natural, and then that reminds me that the ln is the natural log. So if you take a look at your calculator, you'll see that you have an LOG button and an LN button. Most calculators can only do log base 10 and log base e. Most calculators can't figure out what log base 2 of 6 is. We'll talk later on how to handle that, but generally we are limited to those kind. So if you continue to look at your calculator, you'll notice that the second to your LOG button is 10 to the x. and the second of your ln button is e to the x, that's because log base 10 of x and 10 to the x are inverse functions of each other. Similarly, e to the x and the natural log are inverses of each other. So if you ever forget which one's base 10 and which one's base e, well, you can kind of just look at your calculator and it'll tell you. Well, we've had our intro to log functions. Now we're actually going to talk about the graph and graph it. So I have general properties for log functions. Just like with the exponential functions, these properties are true for parent functions only. We know that when we transform things that these our domain and asymptote, things like that, are going to change. So for our basic f of x equals log base b of x, where x is positive, b is positive, and b is not 1, the domain is 0 to infinity. And the range is negative infinity to positive infinity. If you think back to our properties for exponentials, the domain for the exponential was all reals, while the range was 0 to infinity. Recall that with inverse functions, the domain and the range switch, and you'll notice that that's happening right here between the exponential functions and the logarithmic function. A logarithmic function is going to have an x-intercept of 1, 0, a vertical no y-intercept, a vertical asymptote on the on the y-axis. So kind of going back to my parallels with the exponentials, exponential had no x-intercept and had a y-intercept of 0, 1 and had a horizontal asymptote on the x-axis. So you'll notice that everything's just switched. Instead of a vertical on the y-axis, we had a horizontal on the x-axis. Instead of an x-intercept at 1, 0, we had a y-intercept at 0, 1. We're that ordered pair where we switch the x and the y values. So everything that we've learned about inverses is kind of being reinforced here. When our base value is greater than 1, the graph of our logarithmic function will rise from left to right. It looks like this. And when our b value is between 0 and 1, the graph is going to fall from left to right, like this. And logarithmic functions, like exponential functions, are 1 to 1. Any questions? Just a note here that since log base b of x and b to the x are inverses of each other, if we were to graph them, the two graphs would be symmetric about the line y equals x, which is just our third property of inverse functions. All right, so we want to graph f of x equals log base 1/2 of x. This is just a parent function, right? Because all I have is log, a base number, and an x. That's it. So this is a parent. Sometimes people think that it's not the parent just because there's so much already written down that they feel like there has to be more happening, but it's not. As I mentioned, most calculators cannot evaluate logs other than our natural and common log. In cases where we want to graph one that's different, we're actually going to use our exponential inverse function to help us. So the first thing we want to do is identify the exponential inverse function. And don't make it hard. It's whatever your log base is raised to the x power. I always clearly denote that this is the exponential inverse. So f inverse of x is going to be equal to 1/2 to the x. And I make sure I write it down so I don't think that these points that I'm going to write now are the actual points that I want. We're going to get 4 points for this exponential function. And we did that before by just making an xy chart. We chose our x values to be -1, 0, 1, and 2 always. And then we find our corresponding y values. 1/2 to the -1 is 2. 1/2 to the 0 is 1. 1/2 to the first is 1/2. 1/2 squared is 1/4. But these are not the points that we want to graph. We're trying to graph f of x equals log base 1/2 of x. And these points are for 1/2 to the x. What we're going to do to get the points we actually want are to interchange our x and y values, because that's what happens with inverse functions. The x and the y values change. For f of x equals log base 1/2 of x, we want the points 2, -1, 1, 0, 1/2, 1, and 1/4, 2. Questions on anything I did there? Let's plot these 4 points then. Remember that your logarithmic function always has a vertical asymptote on the y-axis. Oh my gosh, I just thought of something. This is just like some other little gimmicky thing to remember. Oh my gosh, how have I never thought of this before? Look, exponential functions have their asymptote on the x-axis, right? Look, they both have x's. So the exponential is on the x-axis, and then the logarithmic, its asymptote is on the y-axis. Well, look at the g and the y. They both have like the loops on the bottom of them. So if you're having trouble, remember where the asymptotes go. Maybe that helps. All right, plotting my points. 2, -1. 1, 0. 1/2, 1. 1/4, 2. We know with asymptotes that one end of the graph always has to tend towards the asymptote, and it's going to be the end that's already close to the asymptote. And there we go. Questions on the graph of f of x equals log base 1/2 of x? All right, let's try some with some transformations. We want to graph each logarithmic function by transformation, state the domain and range in interval notation, and identify any asymptotes. Make sure on the take-home quiz and stuff that you are doing these by transformation. My online students, because they're a little ahead, they were not doing it by transformation, and they were just getting -4 right off the bat for not doing it by transformation. So please make sure you're doing that. All right, well, we have to identify what the transformations are and how many we have and all that stuff. We want to start by identifying our parent function. And our parent function is going to be log, and then a base number, and then just x every time. So our base number this time is 4. So our parent function is g of x equals log base 4 of x. How many transformations do we have?
One.
Just one, right? This minus 2 on the inside. What does a minus 2 on the inside of our function tell us to do?
Horizontal shift right.
Great, we're going right 2. All right, we have our plan. Now it is time to execute our plan. Is log base 4 one of the ones that you can do on your calculator?
No, it's not.
No, it's not. Our calculator only does log base 10 and log base e. So we're going to have to use our exponential inverse to help us get points for our parent function. Well, first thing we need to do is decide what that inverse function is going to be. What is the inverse of log base 4 of x? All we should have is a number raised to the x power for an exponential function.
4 to the power of something equals x.
It's just going to be 4 to the x. Just going to be 4 to the x. Remember that our exponential base and your logarithmic base are always the same number. A parent logarithmic function is just log base x. A parent exponential function is always just your base number raised to the x. All right, so now we need to get some points for this exponential inverse. Making an XY chart using x values of -1, 0, 1, and 2. And then we find the corresponding y values. 4 to the -1st is the 4th. 4 to the 0 is 1. 4 to the 1st is 4. 4 squared is 16. These are not the points that we want to graph. We're just using these to get the points that we want to graph. To get the correct points, we now want to interchange the x and the y values. So the points for g of x equals log base 4 of x are 1/4 -1, 1, 0, 4, 1, and 16, 2. Questions on anything I have done so far? All right, let's graph it then. All of our logarithmic functions have, or the parent one, have a vertical asymptote on the y-axis to start. And then we'll plot our points. 1/4 -1, 1, 0, 4, 1, and 16, 2. One end of our graph has to tend towards the asymptote. It's going to be the end that's already really close to the asymptote. There we go. You'll see that logarithmic functions grow really slowly. Sometimes when the base is a fraction, it might look like it's growing fast, but typically logarithmic functions grow very slowly, while exponential functions, they grow very quickly. And again, I'm assuming that the base is greater than 1. Those fractions are a little weird. So, all right, there's our first graph. We're ready to transform it. There's only one transformation, and that transformation is to shift it to the right 2. Is that going to affect our x or our y coordinates?
X coordinate.
X. Yeah, we're just going to add 2 to the x. We get the points 2 1/4, -1, 3, 0, 6, 1, 18, 2. Let's talk about the asymptotes. I have a vertical asymptote. If I shift my graph to the right 2 units, should I be shifting that asymptote as well?
Yes, because it's a vertical asymptote being shifted horizontally.
That's right. Just like a horizontal, I'm sorry, other way around. Just like a vertical shift affected our horizontal asymptote with exponentials, a horizontal shift is going to affect our vertical. I need to keep the space in between this point right here and my asymptote like the same. And if I don't move my asymptote when I move my points, that's not going to be the case. Another common mistake that I see when people graph these are they don't like give me the tail end here of the graph, that they'll just stop at the last point. I gotta have this tail with the arrow on it. So do not just stop at whatever that is, 2 1/4, -1. Questions on the graph there?
I got kicked out for a second. Can you just scroll
Stop.
up and I can see the points?
Yeah. 1 sec.
So you just added 2.
You got it.
to the right.
Normal transformation. We want to identify the domain, the range, and the vertical asymptote of our final graph there in red. What is the domain?
Two to positive infinity.
You got it, not including 2 to positive infinity. And then the range?
Negative infinity to positive infinity.
Correct. The range for a logarithmic function will never change. It'll always be all real numbers.
Same.
Lastly, we want the equation of our vertical asymptote. What's that going to be?
X equal to.
X is equal to 2. There we go. Questions at all? Next, we want to graph h of x equals the natural log of x plus 5. Are there transformations here?
Yes.
Yes.
One shift upwards.
Just one, though, this plus 5. So I know ln of x looks so much different than that log stuff spelled out, but that's just a log. And if you want to think to yourself, my thought bubble, that this is log base e of x, hey, that's fine with me. Since we're going to be graphing by transformation, let's write out our plan. We want to start by identifying our parent function. What is that parent function going to be? Our parent function is just always log a base in x.
So h of x equals ln of x.
You got it. I know we're used to seeing it like log base e of x, but it's just natural log of x. If you need to think it or even write it, I don't care. But I need you to know that log base e and a natural log are the same thing. Next, we want to identify our first transformation. We said we had a transformation of plus 5. And Anthony already told us that that's going to be up 5. We have a plan. It's time to execute. We want to get points for our parent function, which is natural log of x. Is that one that our calculator can handle?
Yes, actually.
It is. So we actually don't need to do that additional step of finding the exponential inverse. All right, no exponential inverse is needed here. We'll simply make an XY chart. What do you know about our options on the X's we can choose?
That it tends to be more horizontal than vertical.
Well, that's true, but is there a restriction? Can I choose any numbers I want for X? Can I do the same ones I did for the exponentials? Can I do -1, 0, 1, and 2? Let's take a look at our properties of logs, or even just our definition of log. It says that X has to be strictly greater than 0. The argument of a log has to be positive. Has to be. So this is kind of like the third thing we can add to our list of domain exceptions, right? Remember, our domain is all real numbers unless we have a variable in the denominator of a fraction under an even index radical, and now we can add to that inside the argument of a log. So we have like a third one here. The argument of a log always has to be strictly greater than 0, and they stated that in the domain, that our domain is from 0 to infinity. So when we go to make this XY chart, we have to choose X values that are positive. That's our only option. We've talked that logarithmic functions tend to be slow growers. So I would spread out what I choose for X. Like, right, my graph paper goes to 10. I'm probably going to go all the way to 10. So I'll choose a half, 1, I don't know, and then like 5, and I'll do 8. I won't go all the way to 10. Here we go. And then we're just going to plug it into our calculator to get the corresponding Y values and then transform it. So I want to make sure that everybody can get the first one, and then I'm going to let you guys, I'm going to actually put you in groups and breakout rooms and let you guys finish this up together, but I want to make sure everybody's comfortable with their calculator. So let's find out what natural log of 1/2 is. I don't want to leave you in a breakout room unable to use your calculator. So did anybody get a number for natural log of 1/2?
Is it a decimal? Is it negative 0.69 or negative 0.7?
Anybody else get that?
Yeah, I got that.
Okay, actually, did everybody get that? Because again, I want to make sure that you can properly use your calculator.
Yes, I also got that.
All right, so I am going to put you guys in breakout rooms, which just means that you're going to have like a handful of you together in your own little video chat where you guys can work through this problem together. And then I will bring us all back together to talk about the final answer. You guys should be able to like screen share with each other and everything like that if you choose to.
Cool.
Yeah, my calc students like it a lot. All right, we'll put 4 of you in a group. All right, I'll see you guys in a little bit. I'll probably give you like 8 minutes.
I got 160.
160 decibels.
I got that too.
There we go.
Okay, I'm not quite sure what order you went in for the calculator.
All right, let me look at you. Let me look at you in your calculator. Hold on, I gotta make you bigger. I can't see. Okay, so Anthony, what you're gonna have to do in your calculator is you're gonna have to do 10 to the 4th first, divide it by 10 to the negative 12th,
That
then
is
hit
what
your
I did.
log button, and then hit times 10.
Okay, so I have the log button, not 10 to the x.
Correct.
So 160. Okay.
You got it. Anybody else? Our next application has to do with the magnitude of an earthquake on the Richter scale. We're going to be using the formula M equals 2/3 log of E divided by E sub 0, where M is the magnitude
of the earthquake on the Richter scale. Please know that that's unit free. We just, we're just going to get a number 2.1, and then that's just it. There's no unit. E is the seismic energy released by the earthquake, and we measure that in joules. E sub 0 is the energy released by a reference earthquake, and that E sub 0 is always going to be 10 to the 4.4 joules. On May 3rd, 1996, Seattle experienced a moderate earthquake. The energy that the earthquake released was approximately 1.12 times 10 to the 12 joules. We want to calculate the magnitude of this earthquake on the Richter scale. We'll round to the nearest tenth. Well, they gave us E, they gave us E sub 0, we're just plugging it in. M equals 2/3 times log base 10 of 1.12 times 10 to the 12th over 10 to the 4.4. Now, unfortunately, this one in the argument doesn't clean up so nice. I don't really want to get a decimal, or well, I don't really want to write out 1.12 times 10 to the 12th. I mean, that's like trillions. We don't really want to have to write all that out. So we're just going to put it into our calculator as is.
Your cat wants to join.
Can you see her? Oh my gosh. This is the one that's always on the videos, meowing. She always has to be in my face when I'm trying to work on the computer. Cats.
Oh my god.
She's just gonna lay right on it now. All right, so I mean, you don't have to be a seismologist to know something about earthquakes. We should be getting a relatively small number, right? The earthquake that's supposed to rip California off the west coast is supposed to be like a 10. So we should be looking for something below a 10. And it said a moderate earthquake, so I think, like half of that maybe.
I got 5.1.
Yeah, that seems reasonable to me. Anybody get anything different?
I got a negative value.
Then you definitely plugged in your calculator wrong. So you got to start on the inside with your calculator. You got to do 1.12 times 10 to the 12. Divide that by 10 to the 4.4. Then hit your log key. Then multiply it by 2/3.
I also got 5.1.
I think I didn't put the 10 to the 12 and the 10 to the 4.4 in parentheses.
Got it.
Yeah, so 5.1.
5.1. All right. Anybody else?
5.1 joules. So what is
No,
the
it's not joules.
unit?
There's no unit. There is no unit. It's just a 5.1 on the Richter scale. No unit. Oh, anybody else? So I want to take a look. That might be the end of the material on our test, this next test. I want to take a look real quick. Oh, by the way, I think since I've talked to you last, I did go through and then edit everybody's exam. So you might have seen some changes in scores on your exams. I also got all the bonus in and everything like that. So if I'm not totally caught up on all my grading, I'm really, really close. There might be some that trickled in later. Oh, no, one more section. So properties and logs, we'll do that on Wednesday. And then, so that means that next Wednesday, we will not have class and you guys will be taking an exam. And I'll do that 48-hour window again between Wednesday and Thursday next week for that. So,
And you said in your email, like whatever homework like wasn't finished, we can go back and do it for 40%.
yep, that's true for all of them, all the way back to the beginning.
And do you have to open those, or are they like
Nope.
already?
It's already ready to go. Now, what'll happen is you'll click, and maybe you even click on review or something like that, and then it'll say, do you want to go forward to change points? So you got to be careful because it gives you an option to practice without changing your score or change your score. Make sure you click the one that says change your score. Otherwise, students will email me mad that they worked on 50 problems and it didn't change their score at all. So make sure you hit.
Okay.
Anybody else? Anything? All right. Well, then have a wonderful day. If anybody wants to stick around for office hours, I will be here.
Thank you.
Hi, thank you.
Bye.
Have a good day.
Have a good day.
Thank you.